In this video we're going to talk about integration by parts. We're going to go through the proof of the formula and some classic parts examples. Um, so let's see. So basically integration by parts is the integration equivalent to the product rule for differentiation. It's basically finding the integral of the product of two functions. An example of this can be x times e to the x. And, anything along that nature. So, in general, it is f of x. I'm gonna drop the of x. All these functions are functions of x. So I'm just gonna write fg prime equals f prime g plus or fg quantity prime equals f prime g plus fg prime, and that's the product rule for differentiation. So basically we want to find the integral of the ultimate goal is to find the integral of two functions being multiplied together. So we take the integral of both sides, and let me just do that on this line. Dx dx, and obviously we can, well, from here, let's see. Well, the left side, this side, is just the integral of the derivative, so that this cancels out. That's just fg. The right side, let me just rewrite it. F prime g, we can split up into two integrals like that. And from here we can move this guy over to the left hand side. Let me just copy him, and I'm just gonna move this to the right, to the left, because that's how it's normally written. Like that. So it's fg prime dx equals fg minus the integral of f prime g dx. This I'm gonna do a little bit of substitutions here to put it in a more standard form. We're gonna make u equal f of x, and therefore du is equal to f prime of x dx. And another substitution, we're going to do v equals g of x, and dv equals g prime of x dx. Okay, so let's plug these relationships into this expression. So this f turns into a u. Then we have g prime dx, which is dv. So what did I do? Okay. Yeah. G prime dx, I think it should say. Yeah. It's what I should have said, rather. So the left side turns into u, the integral of u dv. And the right side, we replace f with u, g with v, and then we have f prime dx, which is du, and then g is v, so this is v du. And this is the standard form of integration by parts. Now, but what does this mean? It's kind of hard to see what it means right off the bat, and I'm just going to do some very extremely classic examples of integration by parts. If you're doing parts, you're going to do all three of these examples. It's pretty much a given. Because they just show up all the time. So the first one it will just be, let me just, example 1. Let's see, it will just be the integral of x times e to the x dx. And actually, I think I'm going to switch it up a little bit and make this a 4. Doesn't matter. It could be x, it could be 16, doesn't just number. So, basically what you do is you have to sort of relate this to the u dv form on this left. And this is what it boils down to. You pick a u, this is what you pick. You pick a u and you pick a dv. That's what you pick. And when the u you differentiate and the dv you integrate. So, and it's your choice. We can pick u is equal to x or u is equal to e to the 4x. Doesn't matter. But typically, the way it's typically done is you set u equal to the function that quote unquote gets less when you differentiate it. So if you set u equal to x, then du is equal to dx, and that's just because du dx is equal to 1, and then you quote unquote multiply both sides by dx, and you get that. So we picked our u, and therefore we have a du. Now you don't pick a v, you pick a dv. That's important here. You pick dv because if we're comparing this integral to the left side and our u is x, then everything else is dv. So e to the 4x dx is our dv. So let's see, dv equals e to the 4x dx. And now we need to get a v. So we integrate both sides of this, and what's the integral of e to the 4x? Well, that's 1/4 e to the 4x. This, you can forget about the plus c's. They don't matter in this case. And alright, so now we have that. We basically just go over this again. You pick a u, you differentiate, and you get a du. Then you pick a dv and you integrate and get a v. So now we just follow this formula: u times v minus the integral of v du. So u times v is 1/4 x e to the 4x minus the integral of v, which is 1/4 e to the 4x du, which is dx. Now we can evaluate this again because now we have a simple integral to do. Integral of e to the 4x. So an integral of e to the 4x is just 1/4 e to the 4x, but 1/4 e to the 4x times 1/4 is 1/16 e to the 4x. And then of course you have your plus c. And actually, you can go one step further and factor out this guy. There we go. That's your answer. And you could check this by differentiating it, and what have you, plugging it back in, and it's correct. So that's our first simple example. Now, next example 2. I don't remember. Example 2. Okay, so next one is similar to this one, and except it's it's x squared e to the 4x. Same thing. Pick a u that'll quote unquote go down. So u equals, now it won't always be the case that it will do this, but sometimes it's not obvious which one you pick. Sometimes it really doesn't matter. In fact, all the times it doesn't matter. But it's easier in other ways. So we pick a u is equal to x squared, du is equal to 2x dx. That dx is important. Oops. And let's see. So now we pick the u. Now we pick a dv. So what should we pick? Let's pick for our dv? Well, we used up x squared, so everything else is dv, e to the 4x dx. now that we have our dv, we can find our v by integrating both sides, and we get 1/4 e to the 4x, and that's it. Now we just use the formula, this one up here, which you've hopefully written down, u times v, which is 1/4 e x squared e to the 4x minus the integral of v du. So I'm just multiplying v du, and it's x e to the 4x dx, and of course 2/4 simplifies to 1/2. So this is what we have. This is our first part to the integration by parts. Now we have this to deal with, but we've already done this integral before, so you can actually go through this again, the same process, or you can just say that, I'm just going to make a new line, that integral is equal to this. I'm going to put it in the plus e at the end. Say, well, that we found before that this integral was equal to this, so you just replace it, and it'll be the same no matter what. So now you distribute this 1/2 through, well, negative 1/2. Let me make a new line. This is negative 1/8, and this is plus 1/32. There. And we can go one step further. Oh, plus c. We can go one step further. Factor out a 1/4 e to the 4x, and we are left with x squared minus 1/2 x plus 1/8. That's it. Oh, and then plus c. There. And that's it. So that's our answer right there. If you have, you can keep doing this process. If you have integral of x to the n times e to the 4x, you just do it n times. You just do the same process over and over again until the x term vanishes, which it eventually will, if it's a polynomial. And that's it. And there's a whole table method to do these types of integrals, but I'm not a big fan. I'm not a big fan of other methods to do the same thing, unless the other methods are like used as equally as the first method. Alright, so one last example. I'm just going to erase all these e to the x examples. Example 3. This example comes up a lot. Actually, it comes up a lot when you do differential equations, Laplace transforms. This integral comes up a lot, and a lot of people forget how to do it. Cosine of x dx, and yeah, this one is actually extremely interesting. So we're going to do the same thing. We need to pick a u and pick a dv. Now it's not obvious at all which one should be u and which one should be dv in this case, because we said before, pick the u that gets, quote unquote, gets less, but neither of these functions get less when you differentiate. They just change, or in the case of e to the x, they don't change at all, and with cosine they go back and forth. So usually, I mean, it doesn't. This case, it really 100% does not matter which one. Either way is just as easy, and will do the same, get you to the same place. But I pick u equals e to the x. So then du equals e to the x dx. Again, don't forget about that dx. So now we have to pick our dv like before. Our dv is everything else, which is cosine of x, dx. And okay, there we go. And our v is then the integral of cosine of x dx, which is sine of x. That's it, sine of x. So now we plug it into there, and we get e to the x sine of x, because u times v is e to the x sine of x, minus the integral of v du, which is e to the x sine of x. No, minus the integral of v du. Yes, that's right. Okay. So now this is our first part, and this is the integral we now have to do. We need to do parts again. So now we pick our u again is equal to e to the x. Our du is equal to e to the x dx. Our dv is equal to sine of x dx. And our v is equal to negative cosine of x. Now we take this. Again, big, huge cause for mistake is not factoring this negative in. In fact, sometimes to stop myself from forgetting that is to just put the negative in for u right here, so it's taken care of. But I didn't do it this time, and I'm going to go back and change it. So remember, huge factor, don't forget about that negative. So u times v, which is going to be negative e to the x cosine of x, minus the integral of v du. Now minus makes a plus. So plus the integral of e to the x cosine of x dx. Now we factor this minus. This is what I was talking about before. You factor the minus, this goes to plus, this goes to minus, and obviously I'm going to fix this up. There. So now this is what's interesting. We're back to where we started. This integral is this integral. So obviously you can't keep doing this, or else you're just it's gonna be an infinite loop. But the really interesting thing is you say, well, what is all this jazz equal to? Well, remember from the beginning, it's equal to that, your original integral, e to the x cosine of x. And this integral is on the right-hand side over here. And let me just do an aside. In fact, let me open up a new one. This is completely analogous to I'm gonna just bring it up here. This is completely analogous to if you had let's say x equals y plus z minus x. That's exactly what's happening. Your integral here is your unknown, and you basically solve for your unknown. So you move this x to the left side, and you get 2x, then divide by 2. Divide by 2, and then you found your x. That's exactly what's going on here. We take this whole integral and we add the integral to both sides. So it gets rid of this one, and then now you have 2. So then you just divide by 2 and you found your integral. Now we have that the integral is equal to this expression, and actually I can pull out this e to the x, and there you go. So in the end, it boils down to solving it algebraically, which is really actually interesting. So I'm just going to box that in. So that integral comes up quite a few times, and it's always annoying. Eventually you'll be able to do these, to see that and do that, you know, with no big deal. A lot of the times people think that that's really confusing, but you'll get it. That's pretty much all I have to say on integration by parts. It's a very robotic process. Really isn't too much thinking involved, other than the fact of thinking what the derivatives are and what the integrals are, and you know, picking which one is to pick as u, which one to pick as dv, and actually I don't have this in my notes, but I'm thinking about it now. You can using integration by parts, you can find the integral of the ln of x dx. Everyone, hopefully you know by now, that the derivative of ln of x is 1 over x. But the integral of ln of x is actually different, and this is the trick here. And this is completely just like happening right now. I don't have this in my notes. So you set u equal to the ln of x, therefore du is equal to 1 over x dx. Now, what's your dv? Well, remember, dv is everything else. So dv is dx, and your v therefore is x. So now we have x ln of x from u times v minus the integral of v du. Now x times 1 over x dx is equal to just dx. And what's the integral of dx? Well, that's x. So we have the integral of ln of x dx is equal to x ln of x minus 1, if you want to factor out an x. Otherwise you can leave it like this. So pretty cool. And obviously there's a plus c, but you know, no, not but, you know, that plus c is actually extremely important later on in differential equations. So don't but, you know, the c. The c is important. So, and that's pretty much all I have to say. Thanks for watching. If you have any questions, leave them in the comments, like, subscribe, all that jazz. See ya.